Pleasure to welcome Hiro Lee Tanaka, who will talk about broken lines and Floer theory over spectra. Please go ahead.
All right, well, thank you very much for the introduction. Thank you to the organizers for the invitation. I wish that I could actually be there with you, but this is the next best thing. So I'll try to do my best to make a good talk so that I can make up for the fact that I'm not enjoying good Barcelona food. Okay, so before I go any further, most of the work that I'm going to talk about is joint work with Jacob Lurie. There's always, a question of whether to start with some basic math or whether to start with motivation. So let me just jump right into the math, and then I'll give the motivation actually right in the middle, because I think the beginning is quite accessible. So let me begin with a basic and a biased review of some Morse theory. Okay, and this is not the Morse theory as most topologists would use it, but I'm interested in the algebra that emerges from it. Okay, so what we're going to fix is we're going to fix some smooth compact manifold, capital X, and we'll fix some generic smooth function f, along with a Riemannian metric that I'll call lowercase h. And so as usual in Morse theory, I want a genericity of both f and h, so that in particular, near critical points, f looks like a quadratic function. So I'll use that in just a moment. But out of this data, we can construct a chain complex that I'll call the Morse chain complex of x. This depends on the data of f and of h, but I will omit that from the notation. So how is this chain complex constructed? Well, first, let me just draw an example so that we can have a picture to keep in mind. And I apologize for people who have seen this talk before. Even though it's 75 minutes, much of it will be kind of familiar to you. So here's an example of x being S2. That's just some sphere. It's embedded in R3 in an interesting way. And I'm just going to take f to be the usual height function to the real line. And so as you can see, this particular function has 4 critical points that I will label with these black dots. Okay, so what is this Morse chain complex? I'm going to define it as follows. So this Morse chain complex, well, the chain complex, so it should be given by a pair of data, first a graded abelian group, and then a differential on this graded abelian group. So what is the graded abelian group? For simplicity, I'm just going to take copies of Z mod 2Z. I'll tell you the grading in just a second. And there's going to be a copy of Z mod 2Z for every critical point, lowercase x, in F. So that's my notation, crit of F for the set of critical points of F. So as you can see, as a Z mod 2Z module, this will have 4 generators. So what are the gradings of each generator? Well, by my genericity assumption, as you know, near every critical point, f is going to look like some quadratic function. So for example, near this critical point, it could look like the quadratic function called negative x1 squared minus x2 squared. Near this critical point, f is going to look like x1 squared plus x2 squared. And near this critical point, it'll look like x1 squared minus x2 squared. Okay. By definition, the index of a critical point x is just the number of negative signs in this quadratic expansion. So we have a point of index 2, a point of index 1, and a point of index 0 in this example. And what I'm going to do is I'm going to shift, and I always get the convention wrong, so please forgive me. I'll just write plus or minus the index of the critical point x. So that's the grading that everything is in. Okay. And as I mentioned before, of course, a chain complex, I need a differential. So how do I define the differential? So let's say that I have some critical point, say x. And this is where the plus or minus is going to save me because I don't need to get the gradings right. So what is the differential of x? Well, it's going to be some summation over a bunch of critical points whose index is 1 away from the index of the point x that I'm taking a differential of. And so what is the coefficient here that I put in front of that generator y? Well, what I do is I'm going to actually compute the number of gradient trajectories let's say from x to y. If I did from y to x, the plus or minuses would all change sign. Okay. So for example, let's say that I have a critical point called x here and a critical point called y here. Y is the only critical point of index 1, and x is the only critical point of index 0. But either way, the differential will only have coefficients in front of y. These other critical points are indexed 2 away, so I don't find those in this summation. And so what are the gradient trajectories from x to y? Well, there's one here in the foreground, and there's one here in the background. So in this particular example, the differential is going to be 0 here. Okay, so in this example, del x equals 0y, because I'm working over z mod 2c. Okay, and then a theorem here. So if I were to write out this chain complex, I'd have a chain complex with 2 generators in degree 2, one in degree 1, one in degree 0. And if you work out the differentials of everything, the first differential is 0, and these two are non-trivial differentials. There's exactly one gradient trajectory going that way and one going that way. And if you computed the homology of that chain complex, you would recover the homology of S2 with Z2 coefficients, Z mod 2Z coefficients. And so there's just a theorem that this actually gives a pretty finite model for computing the homology of your compact manifold X. So in fact, the homology of your manifold X with Z mod 2Z coefficients, let's say, so I'll just put that in parentheses because I neglected to write the semicolon here, turns out to be isomorphic to the homology of this Morse chain complex. Okay, so this is purely classical. This is not the part that's joined with Jacob. But the way that I always like to begin this talk is by asking, wait, hold on a minute. Why is this a chain complex? So why is it true that the differential squares to 0? Okay, so y is del squared equal to 0. And this is one of my favorite proofs. It's quite simple. So what we do is we realize, okay, so let's first write out what del squared x is. So it's going to be del of the summation of the number of gradient trajectories from x to y, coefficient y. And so this is going to be some summation over the number of gradient trajectories from x to y times the number of gradient trajectories from y to z. And this product is going to be the coefficient in front of some generator z, where the degree of z will be the degree of x plus or minus 2. It'll be 2 degrees away. Okay. And so what we're going to do is we're going to realize the set. So the set of pairs, a gradient trajectory from x to y and gradient trajectories from y to z, so the set of such pairs, as the boundary of a compact one manifold with boundary. And of course, it's one of the first theorems of differential topology, that if you have a compact one manifold with boundary, it has an even number of boundary points. And as such, when you count this, mod 2, this coefficient in front of z is going to be 0, and hence del squared is going to equal 0. And so the question is the boundary of what compact one manifold? And so the reason that I started out with this picture is because you can actually see what's happening here. So let me choose an example of a z. So here's an example of a critical point that's indexed 2 away from the critical point x. And here's an example of a gradient trajectory from x to y, followed by a gradient trajectory from y to z. So that's the kind of thing that'll appear in the set that we're counting in the coefficient of z. What we realize is that this broken trajectory, so one that passes through y, looks very close to a different gradient trajectory, which I'll draw here in green. Some gradient trajectory that goes directly from x to z. And what we realize is in the situation where x and z are indexed 2 apart, there's actually a one parameter family of such gradient trajectories. Okay. And so clearly, if I take this one parameter family, it's an open manifold, but it clearly wants to have a compactification or some sort of boundary, which is that in the limit, as these trajectories approach the point y, this green trajectory becomes a broken trajectory. And if I were to move these green trajectories the other way around towards the background of my picture, it would converge to a different pair of broken gradient trajectories, the one found by going around the back here and then going from y to z. So in fact, what we realize is that this thing is the boundary of a compact one manifold, namely the set of all gradient trajectories from x to z. Okay. So maybe what I should say is actually the set of all gradient trajectories from x to z admits a compactification. This compactification has the structure of a one manifold, and the boundary is precisely the set that we're counting to describe the coefficients of z. Okay, so that's a proof that del squared equals 0. Are there any questions at this point? Okay, so the lesson that I want to learn here is that it's fruitful to consider broken gradient trajectories and add strata to the moduli of gradient trajectories. It's by adding the strata that I get this compactification, and that's how I see this proof that del squared equals 0. So that's clearly pretty slick. All right. So what I'm going to do now is I'm going to apply this lesson when x is a point. Okay, so R0. And so what I want to do now is I want to study the moduli of gradient trajectories inside of x. And so this is a great example because I can now be more precise about some of the geometric things that I've said earlier. So, okay, so of course, what do I mean by a gradient trajectory? Well, by a gradient trajectory, let me be finally precise. I mean a smooth function gamma from R into x, satisfying the gradient differential equation, which is that if I were to take the velocity vector of this trajectory at a time t, I want this to exactly equal the gradient of the function that I started life with at that point gamma of t. What function do I choose on capital X? Well, x is a point. So up to translation, there's a unique function that I can put on x. Of course, the gradient depends on a Riemannian metric. X is a point, so there is a unique Riemannian metric that I can put on this zero-dimensional manifold. So this is completely well defined. And one thing that I want to point out here is I lied to you earlier when I said that I was counting gradient trajectories from x to y. Why is this a lie? Well, if you look at this differential equation, it's clearly translation invariant in the domain, right? Once I solve an ODE like this, it's up to me where I want time 0 to be along the trajectory. So when I have this green gradient trajectory from x to y, it's up to me whether I want this to equal gamma of 0 or whether I might want this x out point to be gamma of 0. So actually, this set has a natural R reparameterization action on it called shift time 0. So what I was secretly counting before wasn't the set of such functions that satisfy this differential equation, but the set of such functions modulo the natural automorphism group acting on it. And so what I really want to consider is not the set, but the set modulo R. So what happens when x equals a point? When x equals a point, well, of course, there aren't that many functions from a real line to a point. So this actually becomes a point in the numerator here, modulo R. And it doesn't really matter, but this, of course, is a different point from capital X. But regardless, it's a point modulo R. And of course, this is the stage of life where you really find out what kind of math you like to do. What do we mean by point mod R? The naive quotient is obviously a point, but for me, I'll be taking the stack BR. So this is a stack on the site of all topological spaces. Okay, so if you like, it's a stack that classifies principal R bundles over topological spaces. Okay, so this is what the moduli space of gradient trajectories in a point looks like. It's actually a stack. So now to this, I would finally like to apply my lesson, which is I should actually now consider broken gradient trajectories as well. So what is a broken gradient trajectory precisely? So precisely a broken gradient trajectory is a map from R disjoint union R to X. And let me just for the sake of my sanity, let me just label these components of R. There's the first component, there's the second component. And this should satisfy obviously the gradient differential equation. But if I'm going to write a gradient trajectory that's broken, I'd like the endpoints of gamma to agree whether I'm in the first component or the second component. So I'd like to demand that the limit of gamma of t, as t approaches the first copy of infinity here, I would like that to equal the limit of gamma of t as t approaches negative infinity in the second component of R. Which is to say, if I have this R1 being mapped in by the gradient flow equation, if I have R2 being mapped in, of course, I would like what I approach at positive infinity in R1 to equal where I come from at negative infinity in R2. Okay, so this is the precise articulation of what I mean by a once broken trajectory. And this also has a natural automorphism group, which is it can act by translation on the first factor or on the second factor. Clearly, that doesn't change the limits and it respects the differential equation. So this actually has a natural R2 action that I can mod out by. And in the case that X is a point, again, there aren't very many gammas. There's a unique such function like this. And so this is the stack BR squared. So whatever I mean by learning my lesson when X equals a point, it looks like I'm building a stack that has strata. One stratum on the interior called BR, another stratum codimension 1 called BR squared. And I don't want to stop there. The example that I began my talk with was a two-dimensional example of a sphere. But you can imagine that if I were to take some higher dimensional manifold, and if I took some point of index 0 and some point of index 10 million, there's actually going to be an incredibly high dimensional moduli space of gradient trajectories that go from a point of index 0 to a point of index 10 million. And I can compactify that moduli space by adding corners and corners all the way up to codimension 10 million minus 1. And so likewise, in general, by considering, let's say, k times broken gradient trajectories in my manifold X being a point, we have a stratum, point mod R to the k plus 1, which is, of course, the stack BRK plus 1. And so whatever we mean by learning this lesson of adding all the broken gradient trajectories to get an interesting space, if I apply that to a point, I get some interesting stack that looks like it's made of strata BR to the k for every k. And so this is going to be the central player in today's talk. So this is not really a definition because a stratified space isn't defined by its strata, it's defined by how the strata are glued. But let me just say that the stack that I'd like to talk about today is a stack that Jacob and I have called broken. And again, this is not a definition because I haven't told you how to glue the strata together. I'll give you a rigorous definition when as the lecture goes on. It's the union of BR to the Ks for every non-negative, for every positive integer. Okay, so informally, this is the moduli stack of possibly broken gradient trajectories on a point. I think it's fairly unassailable that this seems just like a natural thing to consider in life. Like Morse theory is natural, it's super useful, and we don't normally think about it for a point because a point is such an easily understandable manifold. But just for understanding the universal structure of moduli spaces of gradient trajectories, of course, you should study that on a point. Okay, so now finally, let me get to some motivation. Why in the world would you be interested in this? And I love that I have an hour and 15 minutes because I can really go into this now. All right, so motivation number one, let's say that you care about Morse theory. Okay, so if you care about Morse theory, here's a good motivation. This is universal. For Morse theory or Morse moduli spaces. So what do I mean by that? So recall that earlier, from the data of manifold X that's smooth and compact, a Morse function F, and a Riemannian metric lowercase h, I ended up making some moduli space that I'll call M bar. This is the usual moduli space. Let's not do anything stacky, of a broken, possibly broken, gradient trajectories. So this is a thing before that we considered, there was a compact one manifold with boundary that we considered earlier. And in general, for example, if X were like 10 million dimensional, this will be some 10 million minus one dimensional compact manifold with corners. And this has a bunch of different connected components, right? Like here, like there's a connected component of trajectories from X to Y. That just consisted of 2 points. There's a connected component of gradient trajectories from X to Z. That was the compact one manifold with boundary. Okay, so this has many different connected components, possibly of different dimensions, but they're all manifolds with corners, and they're at most a dimension of X minus 1. And as I spoke about earlier, because this is a manifold with corners, it's a stratified space, stratified by codimension. And the observation that I want to make is, so any manifold called X has a natural map to a manifold called a point. And this has the stupidly obvious and beautiful property that gradient trajectories in X are sent to gradient trajectories in a point. It's an R equivariant map, if you like, with respect to the gradient flow action. And so it follows that, in fact, there's a space, there's a map from the moduli of gradient trajectories on X to the moduli of gradient trajectories on a point, which is to say, there's a map from M bar to broken, always, regardless of what X, F, and H are. And so the way that you can think about this is like, if your world, if your universe consists only of Morse moduli spaces, broken is kind of acting like spec of the integers. It's like the point that you map to. Right? It's like the terminal object in this moduli, in this category of moduli. And of course, it's wonderful to have such a thing, because if I wanted to understand, say, moduli spaces for not just X, but say X times Y, you can imagine taking a fiber product of the M bars that we get from X and from Y over broken. And so you can prove things like the Kunis formula for homology, at least for Morse homology, if you believe that, if you just run through the math. Okay, so that's obviously pretty nice. It's a natural new object in mathematics. That seems useful, but maybe it doesn't do anything for us. Okay, so here's another motivation. Maybe you don't care about Morse theory. Maybe you care about algebra. So let me observe some geometry that'll get me to some algebra. I actually want to notice that broken actually has an associative operation, a non-unital associative operation. And let me explain what this is. This is nothing more than concatenation. For example, if our manifold X were some actual manifold, like some higher dimensional thing, let's say that I have some broken gradient trajectory from X to Z. And let's say that I had some other broken gradient trajectory that I'll draw in green from, say, Z to W or something. Well, of course, I can concatenate these to obtain a broken gradient trajectories from X to W. So long as the endpoints of my broken trajectories agree, there's always a concatenation operation on this M bar. This M bar has a partial multiplication called concatenate. Well, when my manifold capital X is a point, endpoints always agree. So we just have an honest multiplication on broken. Okay, so this is given by concatenating. I'll just call it M. Just concatenate. And we just heard a talk by Imbar about factorization homology. And it was completely unnecessary for her to talk about things like factorizable co-sheaves on certain stratified spaces, although that is one way to frame factorization homology, no pun intended. Broken is now a stratified gadget with some multiplicative operation on it. And I think in the past decade or so, it's become a little bit fashionable to study sheaves on such a thing with the data of compatibility with M. So it makes now sense to study factorizable sheaves unbroken. So let me say briefly what I mean by that. So, so a factorizable sheaf is a sheaf, let's say a fancy F unbroken with the following data. So once I have a sheaf on a space like broken, there's actually always a canonical way to construct a sheaf on a product of broken with itself, which is namely just the box tensor product of f of f. In terms of stocks, if I have a point called like x comma y on this stack, the stock of this sheaf there would just be f, the stock at x, tensored with the stock at y. Okay. On the other hand, because I have a operation called M, there's another way to construct a sheaf on the space, which is just pull back the sheaf on broken to this doohickey. So on the other hand, I have this natural sheaf on broken times broken, and a factorizable sheaf is a sheaf F together with the data of an equivalence between these two things. Okay, and of course compatible data with the associativity of M, and so forth. So I think this is some conference where I think like the theme insinuates some sort of familiarity with higher structures. So of course, like we know that associativity isn't a property, at least to a homotopy theory. So you want to kind of encode that compatibility everywhere. So that's roughly the kind of data that's being encoded in a factorizable sheaf. And so it's just incredibly natural to ask, hey, what are factorizable sheaves unbroken? And the really amazing thing is we can completely characterize them. And in fact, we get an incredibly familiar answer. So here's the theorem that Jacob and I put up on the archive a few years ago. Okay. So a fixomonoidal compactly generated infinity category C. And to denote the monoidal structure on C, I will write tensor. And so if you don't like, or if you're not happy with using terms like compactly generated, let me just give some examples that you could consider. You could consider topological spaces with direct product. You could consider chain complexes over some base ring R with the derived tensor product over R. And of course, you could also consider a spectra with smash product, if you like. So these are all examples that you can keep in mind. Of course, there's many more. In fact, all these examples happen to be even symmetric monoidal, and that's not necessary for this. Okay, then what's the theorem? So the theorem is that we can classify factorizable sheaves unbroken with coefficients in C. Oh, and of course, a more down-to-earth example would be something like vector spaces over K with tensor product over K. So for example, maybe we have a sheaf of vector spaces unbroken. Okay, that's a factorizable sheaf. Then the theorem is that this category of factorizable sheaves is equivalent to a very familiar infinity category. The category of associative algebras, possibly non-unital in C. In other words, like maybe an informal way to put this is the stack broken together with multiplication. The geometry of that completely encodes the algebra of associativity. Okay. So again, this is the category of non-unital associative algebras. If C is some honest infinity category, so it's actually homotopical in nature. Of course, by associative algebra, I mean A infinity algebra. Okay. And in particular, maps of factorizable sheaves gives rise to A infinity algebra maps, because this is an equivalence of categories. Okay, so if you're interested in algebra, here's actually a cool thing. Turns out that Morse theory of a point completely encapsulates the algebra of A infinity structures. That's pretty interesting. But maybe you don't even care about that. And so here's somehow the real motivation that we are studying this stack, which is this gives is the beginnings of a roadmap to enrich Lagrangian Floer theory over spectra. And so I do not assume that everybody is familiar with this. I mean, we've seen Fukaya categories appear in talks of Jasso, for example, earlier. But let me really try to motivate this point. So if you haven't been listening at all for the last however many minutes, you can tune right back in here, especially if you're interested in stable homotopy theory and new methods for studying stable homotopy theory, because that's kind of where I'm hoping all of this is going. And so let me just say that, so symplectic geometers, inspired by physicists, now have techniques for taking certain symplectic manifolds, capital M, and outputting some stable infinity category that for this talk, I'll call the wrapped Fukaya category of M. Okay, and with some geometric assumptions and structures that one can impose on M, this is honestly stable. It's not Z linear or R linear for some classical ring. For example, you can fix things so that what you associate to a symplectic manifold called a point will actually be the stable infinity category of just a finite spectra, for example. And so what this actually puts into the game is if, for example, there's natural symplectic actions on M of a group, say, all of a sudden there's group actions on these stable infinity categories. Okay. So for example, if you were to be able to find interesting symplectic actions on a point, punchline, there aren't any, you'd be able to find interesting actions on the category of spectra that you might want to study. And one kind of interesting thing that actually happens immediately in this construction is that it turns out that if I construct a stable infinity category associated to M, so let me call this W of M, there's an interesting property that immediately happens, which is that stable geometry enters in a completely different way. It turns out that there's a natural equivalence between the category that I associate to M and the category that I associate to M, but just stabilized. And so, as you know, in classical topology, how do I stabilize? I just take a direct product with R. Right? I just move into higher and higher dimensions. What I'm doing here is just a symplectic version. The cotangent bundle of any manifold is symplectic, and the product of two symplectic things is still symplectic. And it turns out that I mentioned that there's geometric restrictions that I need to place on M. Taking a direct product with T star R doesn't change those geometric restrictions. Which is to say, roughly speaking, that the category of finite spectra is actually, you can think of it as some symplectic invariant associated not to a point, but T star of R infinity. And so, for example, if you have interesting symplectic actions on T star of R infinity, you can try to find them. And you can try to ask, hey, what kind of action does that introduce on the category of spectra? In other words, you can start probing a pick of the sphere spectrum, and in particular, higher homotopy groups. Now, all of what I'm saying is widely expected to be true, but it is dependent on some facts. Like we actually don't know what the stable symplectic automorphisms of T star R infinity are, for example. By some ridiculous accident, it might happen that if we impose all the geometric structures we need on M, this becomes contractible or something. The automorphism space becomes contractible or something, in which case none of this would be interesting. Okay. For example, if we were to consider smooth auto equivalences of Rn, if we put a framing on those, of course, the space of smooth auto equivalences of Rn that are framed as a contractible space, you'd find no interesting actions. Okay. So maybe this is a dead end, but there's actually other things that we can do. For example, you can consider some category of symplectic manifolds with some geometric structures that I'm not going to get into. This is a symmetric monoidal category. And so it's widely expected that this assignment called the wrapped Fukaya category into the infinity category of stable infinity categories is widely expected to be a symmetric monoidal functor of infinity categories. And so in particular, for example, whenever you can find some E infinity or En algebra here, you suddenly have En monoidal objects on the right-hand side. And in some joint work, for example, with Zach Selvin and Oleg Lazarev, we can actually produce interesting examples of E infinity algebras here that produce, for example, localizations of the stable homotopy category that are symmetric monoidal on the right-hand side. So just from purely symplectogeometric considerations, my claim is we are finding out how to construct interesting objects, if not in stable homotopy theory classically, then certainly in this new world of stable infinity categories at large. And so my hope is that this is the kind of thing that hopefully opens up new avenues and new ways to study questions in stable homotopy theory. So that's actually the spiel that I normally would not be able to give in a 60 or 50-minute talk. Are there any questions about my talk at this point?
What about the other way around, like saying something about symplectic side from stable homotopy theory?
Yeah, so that's actually the side that is very easy to do. Sorry, I should say that the expectations are natural and they don't need to be explained too much because typically the wrapped Fukaya category is z-linear, so it's HZ linear. And so as you might imagine, the kinds of invariants that we find then would surely be weaker than the kinds of invariants we find if we have something that's spectral. And so there's already examples of symplectic manifold and Fukaya categories out there. The name to find here is Timothy Large. I think he's still a PhD student at MIT, but even working over, I think, KU, he's found examples of things in symplectic geometry that we couldn't distinguish before using integer invariants, but that we now can distinguish using stable homotopic invariants coming from KU, for example. So the applications to the symplectic side are quite natural. This is just a richer invariant than the usual z-linear thing that symplectic geometers currently know how to do. And so the motivation for studying stacks like broken is in a way that I haven't quite explained yet. It naturally tells us how you construct Fukaya categories over spectra. And I think prior to be frank, Jacob noticing this, I don't think anybody noticed it. Are there any other questions? Or did that answer the question at least?
Sure, yeah, thanks.
Okay, great, thank you. Are there any other questions? Okay. So let me now, motivation 3 prime, I just made a pretty bold claim here. So how would this work? Like what in the world does this have to do with symplectic geometry and Lagrangians? And so let me just give a sketch of how it goes. So in symplectic geometry, so instead of studying, say, these gradient trajectories from the real line to x, somehow this is the thing that defines the differential. And so symplectic geometers know how to define all kinds of chain complexes. What is the thing that defines the differential in their chain complexes? They study maps, I'll just call them U, from a thickened version of the real line. Okay, so here's a picture of R times 0, 1. And the point is, so this is not thickening in the same way that we thicken a cotangent bundle. This is actually a complex thickening. The point is that this is a complex manifold because it's a complex submanifold of the complex plane. And when X here is a symplectic manifold, it turns out it's a basic exercise in symplectic geometry. There exists a contractible space of endomorphisms of the tangent bundle that look like a complex structure that's square to -1. It turns out there's a contractible space of such that are compatible with the symplectic structure. Okay, so let's just choose one of these J's. So it's making X look like a Kähler manifold, but J doesn't need to study or satisfy the integrability condition. So it's not a complex manifold straight up. It's usually not, but it does have some almost complex structure. And that's enough for us to study the holomorphic curve equation. So before we studied the gradient equation, where we demanded that gamma satisfy some differential equation. Here we're demanding that these U's satisfy some differential equation. And it turns out that just like before, we could investigate how gradient trajectories might break into broken gradient trajectories. We can actually study families of such maps and study how they break into a pair of such maps. And in fact, when you look at the moduli space of holomorphic maps when X equals a point, how many U's are there? Again, when X is a point, there aren't very many maps. There's only the constant one, and the constant map is clearly holomorphic. So this moduli space is a point. But we need to mod out by, to make it the moduli stack, we need to moduli space, we need to mod out by automorphisms. What are the automorphisms of this differential equation? Well, there's actually only an R translation automorphism of this complex manifold. And so actually, we see right on the nose that the moduli stacks of holomorphic strips in X is isomorphic to the moduli stack of gradient trajectories in X. Even with these broken strips, there's an R action here and an R action here, you get BR squared. Stratum for stratum, it's the honestly, like, it's not the same stack, but it might as well be. It's clearly obviously isomorphic. So, the holomorphic analog of broken, so the holomorphic strip analog of broken is isomorphic to broken. So you're getting a sense now that if X weren't a symplectic manifold, or sorry, if X weren't a point but a symplectic manifold, you can still make some moduli space of these U's, and this moduli space of these U's would still map to broken. And so whatever we can do with Morse theory, we begin to imagine we can do in this world of symplectic geometry. And so how then do we construct something that looks like a chain complex out of this data? Okay, and so the way that we construct a chain complex out of this data is to make an invariant, like, for example, the Morse chain complex of X, we just note the following. So I mentioned earlier that the moduli space of gradient trajectories, and you can think of this as gradient trajectories or holomorphic strips. It's not going to matter, but maybe we'll say gradient trajectories for concreteness because that's what I assume people are more familiar with. Let me call this map P, the universal map to broken. Well, given a base ring K, what I can do is I can take lower streak of K. So what do I mean by that? But by this, I mean that the constant sheaf on n bar, right? Where the stocks are just the base ring. And the point is, this sheaf is fairly obviously factorizable because K tensor K is K. And so what we can do is we can take a version of lower streak that respects this factorizable structure. And so this is going to be a factorizable sheaf on broken. Okay, say in what is C, say in K modules. So K, it could be an honest ring, it could be a ring spectrum, it could be a sphere spectrum. Okay, and by the theorem from earlier, which is that to give a factorizable sheaf here is the same thing as giving an associative algebra, we realize that this gives some like weird associative algebra that maybe we haven't seen before. So again, because this is an associative algebra, so this is some associative algebra. Okay, and it turns out, so this is a claim that I'm not going to be able to sketch how it goes, but in orientation on this moduli space. So if you've studied things like Gromov-Witten theory before, you know that orienting moduli spaces is somehow the name of the game. So an orientation of M bar that respects concatenation picks out a Morse-Cartan element of this associative algebra. So now we're entering the realm of deformation theory and algebra. So again, what does it mean to be a Morse-Cartan element? It's this, except of course suitably interpreted. Right? This makes sense to ask for any kind of associative algebra. And so the question is, wait, hold on, what does that even mean? And it turns out that this algebra is actually easy to identify. It looks like the algebra of graded endomorphisms of this object that we saw earlier. So this is in the Morse theory setting. If this were in the holomorphic strip setting, I didn't tell you what the generators were, but this would just be a graded object called the direct sum of the generators. Okay, so this is the underlying abelian group of the chain complex, or the underlying K module of the Morse chain complex. And it's a graded object. Right? It's not just graded in the sense of it. Yeah, so I want to consider this as an object in the category of graded things. Okay, and it's a classic. It's like the first example of a deformation problem, at least in homological algebra. Hey, given a graded object, can you put a differential on it? And precisely the deformation problem that you get out of answering that question is you write out the graded endomorphism algebra of this thing, and you realize that giving a Morse-Cartan element of that graded endomorphism algebra is precisely the data you need to put a differential on this. So it's just a classical homological algebra. A Morse-Cartan element of graded endomorphisms of some direct sum of graded objects precisely yields a differential on this graded object. And so the place where like the higher algebra comes in is, so this is of course homological algebra. The analog of this statement is still true spectrally. But the point is, spectrally, it's often really difficult to produce maps of algebras or Morse-Cartan elements of algebras. And the point of all this broken machinery is we reduce it to geometry, that being able to produce an orientation of this guy, which is a question purely in just differential topology, formally by using this factorizable lower Schrick machinery, produces a Morse-Cartan element, thereby putting a differential, quote unquote, on the spectral thing. And the claim is here, when we do this when K equals a spectrum, the sphere spectrum, for example, it won't recover the homology of X, it'll recover the stable homotopy type of X. Okay, so that's somehow like the outline of where things go. All right. So that actually concludes the motivation part of my talk. And now I'd actually like to try to define broken and give a sketch of the theorem. But are there any questions up until this point?
Hey, so just to make sure I understand, so in the case where you're doing this over spectra, the copies of the sphere spectrum with the indices tell you what the cells are, and then the Morse-Cartan elements tell you how to make a spectrum out of those cells?
Exactly. It's exactly how Cohen, Jones, Siegel describe the construction of stable homotopy types out of Morse theory. The algebra is identical.
Cool, thanks.
Any other questions? Joachim, are you telling me something about time, or are you about to ask a question?
No, I was just looking if there's anything in the chat, but there's nothing.
Okay. It's always a bad sign. Okay, so now I actually like to get to some more concrete math. Okay, so let's at least talk about the definition of broken. So if you recall, I gave this very informal definition of what broken was. So now let me actually define it. And so as with most stacks, I'm going to define it as classifying something. So what does a map, let's say from a topological space S to broken, classify? So informally, if you know the motivation, it should somehow classify some family of Morse trajectories parameterized by S, but these Morse trajectories are allowed to break. And so the terminology that we chose for such a family is something called a family of broken lines. And so let me tell you first, at least, what an element of a family is, what a broken line is. So definition. So broken line is the data of in R space, capital L. So some space capital L with an R action, satisfying the following conditions. So first, this is going to be boring. Abstractly, I demand that L is actually just a compact closed interval. It's already boring. I will demand that the fixed point set is finite. So let me tell you the kinds of things that this already excludes. So here's a picture of a compact interval. Just from basic topology, the endpoints have to be fixed points of any R action. And you can imagine that the R action has a bunch of fixed points that say like accumulate somewhere. And that's all that this is excluding. Because of course, in the setting of Morse theory, we often work with finite dimensional manifolds, so you can't have some infinite accumulation of breaks. Anyway. And the second thing is that I demand that the R action is directed. An informal way to put this is that this defines an orientation on L. So for example, you can imagine that there's an R action with exactly 3 fixed points, but where the direction of the R action looks something like this. So this is not allowed. Okay. All right, wonderful. So an example of a broken line, would be something like a closed interval, maybe with some finitely many fixed points, and the R action might look something like that. Okay, so this is allowed. So let me just make a remark here at this point. So an isomorphism of broken lines is just an R equivariant homeomorphism. And so, for example, if I were to look at the category of broken lines, or the groupoid of broken lines, really, how many broken lines are there? Well, there's one for every integer, or for every non-negative integer. Here's a broken line with no interior fixed points. Here's one with 1 interior fixed point. Here's one with 2 interior fixed points. So the number of objects is roughly countable. It is countable up to isomorphism. And what are the automorphisms? Well, to give an R equivariant homeomorphism is to just say, hey, if I choose an interior point here, maybe I shouldn't draw it with a dot. Here's an interior point. It's not a fixed point. I just need to tell you where this goes. And that completely specifies an R equivariant homeomorphism of this guy. So actually, the automorphism group of this is R. The automorphism group of this is R squared, because there's an R component here and an R component here. And so you actually see, at least at the point set level, the categories associated to a point, of course, define these BRK plus 1s. As a category, this is BR to the K, each of these. Okay, so you see this union appearing even at the point set level. And it had better, of course. Okay, so now I need to define for you what a family of broken lines is, which is also quite simple. Okay. All right. Is it true that I have 20 minutes left?
Yes.
All right. Y'all are in for a ride. So what is a family of broken lines? Say over a capital S, that's just a topological space. Is the data of the following. So it'll be the data of some space capital L with a map to capital S. And by the way, is there an audio video lag or is it okay?
No, it looks good to me.
Okay, perfect, awesome. All right, so it's the data of a space capital L mapping down to S. And I'm going to demand that L is in R space. The previous case is going to be when S equals a point. That's what a broken line is. Okay, so such that, so first, the R action is fiberwise. Okay, so in other words, like P is an R equivariant map when S has the trivial R action. Okay. Next, so P is locally trivial as an oriented 0-1 bundle. So what do I mean by that? So if here's my capital S, here's some lowercase s. As usual, I just mean that there exists some open neighborhood U such that, P inverse of U is just going to admit a homeomorphism to U times 0, 1. And oh, right, I should have mentioned, sorry, so condition 0. And, for every point lowercase s, I demand that the fiber is a broken line. Sorry, I should have said that. I apologize. Hopefully that's intuitive for it to be a family of broken lines. Okay, so abstractly, I know that each of these fibers is a broken line. And I demand that there exists a local trivialization. So this actually just looks like U times the interval where, this is completely coherent. So the orientation induced by the broken line structure is just, the same on all of these. Okay, and the final requirement is that P is unramified. So I think this is a condition that's familiar in algebraic geometry, but I don't see it used much in topology papers. So let me precisely say what that means. That means locally on S, P is locally a closed embedding. And the two instances of locally is not a typo. Both instances of locally is required. So let me illustrate the kind of thing that this rules out. So for example, let's say that your space capital S is just this horizontal line. And let me draw right over it, maybe this total space capital L, mapping down to S. And let me draw the fixed point locus of the R action. So if I restrict to a single fiber, of course, there might be some finitely many fixed points. A fiber is a broken line. And you can imagine a scenario where actually this locus of fixed points branches like this. Okay, and this is excluded. Such a picture is excluded by condition 2. Okay. This is because in Morse theory, if you pretend that this broken line represents just like 3 gradient trajectories, in Morse theory, it does not happen that somehow this interior gradient trajectory just disappears to become a constant point. That just doesn't happen. So that's somehow a natural restriction from Morse theory.
Could you please tell once more what should be locally closed embedding? Somehow I'm confused.
Yeah, absolutely. So let me say an equivalent condition, because so equivalently, so let's fix some small enough U So let's look at its pre-image. So that's some cylinder here. And let's look at its R fixed point set.
Mhm.
And so what it means to be locally a closed embedding is actually that we can write this as some disjoint union of a bunch of sets. It's necessarily finite, as it turns out. And I just demand that, so that the induced projection map to U, I guess, that on each component, this is a closed embedding. So it turns out that this is equivalent to this unramified condition.
Okay, thank you.
Yeah. So of course, globally, like it's not a closed embedding from this, right? Because I might have fixed points, that live over, that are in the same fiber. So this projection map into U, like it's clearly not an injection, but on each component, it's a closed embedding into U. Yeah. Are there any other questions? So that's it. So so broken is the stack classifying these things. Oh, right. So what is equivalence of two families of broken lines? It's just an R equivariant map, R equivariant homeomorphism. So this, for example, would be a diagram in the in the groupoid of broken lines, families of broken lines. Maybe it'd be less confusing if I just had a single S, like so. Okay, so that's what an isomorphism of broken lines is. And so now you know what broken is. A map from S to broken is the same thing as giving a broken line, and broken associates to S this groupoid.
So this is a classical stack of groupoids, right?
Yes, one groupoids, exactly.
Mm-hmm.
Yes, on the classical site of topological spaces, on the one category
Sure.
of topological. Yes. Oh, and by the way, it's definitely a stack. You can check everything here is a local condition that glues. Okay, so let me give some examples of these families. And actually, I will have given all examples of these families in some sense. So maybe I'll actually leave up this slide, quote unquote. Okay. So just some examples. So we've seen all the examples over a point, right? Broken lines are the only families over a point. Well, here's one example. Let's let S be just a half ray, a closed half ray. And there's actually a family that I can draw over it that looks like this. So it's a family where on the interior, there's, these are just trivial lines with no interior breaks. And right on the boundary, it develops one break. And let me give you a sense of how to actually write down this family. So the way to write down this family actually is you take the positive octant and you map it down to S using the multiplication map. Okay, so for example, if I have a point called x1, x2, I'll just map it to x1 times x2. Okay, so S is the same as your non-negative real numbers. And what I note is, this is like everybody's favorite example of a degeneration, right? And so what we note is that there's an R action on the total space where T can act by x1, x2 by e to the negative t acting on x1 and e to the t acting on x2. Oh, actually, I flipped the signs. Let's go like this. It doesn't really matter. Yeah, so clearly this respects the multiplication map. And what this R action looks like is, so of course, a pre-image over a given S is a hyperbola. It is an arc of a hyperbola. And what this R action looks like is this. And so generically, that's, these fibers are all hyperbolic arcs with this, free and transitive R action. But on the fiber above 0, when x1 times x2 equals 0, this R action has a fixed point at the origin. And so you see now this interior break developing. And the way that you go from this classical model of a degeneration to make the fibers compact is you just add some points at infinity on these hyperbolic arcs. And that's how you construct this family. Okay, are there any questions about this family? I think it's very nice. It's, it's clearly just a very understandable classical map. They just need to compactify a little bit and you get this family. And so once you have a family like this, you can actually just start gluing families together. So for example, like, maybe I have a family that looks like this and, a family that looks like that again. Then I can, there's an R equivariant map with this image. So maybe like R times S into here, and an R equivariant map with this image. And I can just glue. And for example, I can start getting families of broken lines that look like this. So actually, once you construct this, it's fairly easy to construct newer examples. So with that being said, let me describe some other concrete examples of families of broken lines that generalize this. So further examples, we can let S be the positive quadrant. And we can let the fibers of this now look like, there's exactly, the fiber of the origin has two interior fixed points. The fiber over one edge has one interior fixed point. The fiber over another edge also has one interior fixed point, and the fiber over the interior of this quadrant has no fixed points. So if I were to draw a picture of this, the family would look like this. Two fixed points here, maybe a line of fixed points like this, a line of fixed points like that. And in the interior, no fixed points. So is it clear what kind of family I'm depicting here? Okay, and so of course there's a generalization of this for any dimension, right? Over a Euclidean corner, so R3, for example, there's the analogous thing, right? Where the number of interior fixed points is somehow the codimension of the strata. And so what this gives rise to by definition of broken is we have a bunch of maps called J sub n from the positive n-dimensional Euclidean corner to broken. So we have this collection. Let's say from n bigger than or equal to 0. When n equals 0, this is just a point mapping to broken, and that just classifies the trivial line with no interior fixed points. And so here's just a lemma. So lemma, these maps Jn form a cover of broken. So I used it in stacky language, but this is actually very concrete. This just follows from the fact. So this will follow from the fact that every broken line, regardless of the base and regardless of the family of broken lines, it's locally isomorphic to one of these. So one of the families classified. By some Jn. And the proof of this is pretty natural. So how does it go? Okay. So the sketch of the proof of this lemma goes as follows. So again, this is a local statement. So let's just restrict ourselves to some capital U around some point lowercase s. And let me consider the fiber around lowercase s. Okay. So what we can do actually is by the local triviality condition, we can actually find local sections. So I'll call these sigma i's. So these local sections will have images that look like this. Okay. So I've only drawn one fiber here. but we can shrink capital U as necessary. So shrink U is necessary so that sigma I of U, the images are entirely in the non-fixed point set. So none of these blue slices hit a fixed point. Okay. And so now what you can do is you can ask the following natural question, which is, so for every point, say T on the base, let's look at these points determined by these sections. We can ask, how long does it take to flow along the R action to get from, say, sigma 1 of T to sigma 2 of T? Notice that these sigma i's are ordered, right? They're ordered because there's a natural orientation on these broken lines. And so, for every, I and j, can ask, for the T, well, T is an unfortunate, can ask for some tau, such that, when I act by tau on sigma I of this other point T, it equals sigma j of T. And at this point, you should complain, because if there's like a fixed point between these sigma I and sigma j, then there's no such R. And so the one thing that you need to check is actually this extends to a continuous function with target the extended real line. So what this actually defines is, this defines functions. So let me call this a tau ij. What this actually defines are functions tau I comma I plus 1 from this neighborhood to the extended real line. And in fact, because everything is ordered, and I'm only considering I to I plus 1, you can just make it so that, in fact, this is open here. Okay. And so how many of these are there? So that's just, so this is i.e. a collection of, let's just say, n functions from U to this half-closed real line. Right. Again, by the hypothesis that there's only finitely many fixed points, you only need finitely many sections. So there's only finitely many i's that you can choose anyway. And so maybe there's n functions. So of course, that's the same thing as a function from U to the n-fold product. And by using a standard thing like log or exp, and maybe by reversing orientation, that's just the Euclidean corner. And now just by construction, you can actually check that, so before we had this map called J sub n into broken, you can now just check that the induced map between the restriction of the entire family to U and the map to this pullback of Jn is indeed just a homeomorphism. I mean, it's somehow rigged to be a homeomorphism the way that these distances were chosen. And are covariantly so. So this is just the proof that L restricted to U is homeomorphic to, this line. Oh, okay. What do I do? Let me call this map alpha U or something to alpha U pullback of, the line over Rn classified by this Jn. Okay, so this is a sketch of the proof of the lemma. Okay, so what this tells us is all we need to understand factorizable sheaves unbroken, and in fact, sheaves unbroken, is to understand the transition functions between these Rns. And so now in the remaining 2 minutes, let me just try to convince you why associativity pops out. Okay, so let's let Vn or Vk denote the stock of some sheaf F at this kth stratum. Okay, so how do we characterize these? Well, we can take R0 greater than or equal to 0. This is J0. This maps to broken. If I have some sheaf F on broken, I can pull back the sheaf F. This is a point. A sheaf on a point is nothing more than an object. So this will be called, say, V0. Okay. Now, if I have R1 mapping to broken, I'm going to go a little bit faster because I don't want to go, oh, I'm almost out, I am out of time. Okay, so let me just, so the family that lives over here looks like this. So the stock here, this is a never broken line, so the stock here is going to be V0. This is a once broken line, so the stock here is going to be V1. And the restriction map from this big interval containing the origin to this small interval is going to give me a map from V1 to V0. That's what a sheaf on this looks like. By factorizability, remember this isomorphism by M pull back F is F box times F. We see that V1 has to be V naught tensor V naught. So this is where we get the multiplication map for the associative algebra. And I promised that now if you look at this broken line family, if you look at this open set, restricting to this shaded and interior open set, factoring through these two little thimbles, I promise that you'll find associativity. You get something that looks like this. And to prove A infinityness, you just do this for all dimensions, and you find that the right combinatorics pops out. Okay, so that's a sketch of the main theorem that I wanted to provide today. So thank you very much for listening. Sorry for going a minute over.
Thanks a lot, Hiro. That's very nice. So, are there questions? There's a lengthy question. Victor, would you not just say it yourself?
Okay, oh, sorry, go ahead, please.
No, if you could read it, it's better for me.
Okay, I'll do that.
It's so quite hard to explain it.
Yeah, okay. I have a maybe lengthy question. Your broken lines are like a topologized version of totally ordered finite sets, and that could motivate why factorizable sheaves on broken classify non-unital A infinity algebras. I agree with you 100%. If I understand well, since you did not admit ramifications, units cannot be encoded. That has something to do with it. I'll get to that in just a second. Allowing them in some maybe highly non-trivial way could lead to unital A infinity algebras. Is it possible to add more points to the stack to consider A infinity categories? So I'm going to focus on that last question. So can I get unitality? I think Victor is pointing out that the main theorem that I'm looking for right now stated that factorizable sheaves are the same thing as associative algebras. So is there some way that I can modify the stack broken to get unital associative algebras? I don't know. It's not the same thing as allowing ramifications, I don't think. But this is very related to the Ron space picture, which is how do you modify the Ron space to encode unital EN algebras using factorizable co-sheaves on the Ron space. And I haven't thought about it in the broken case. From the perspective of causal duality, it doesn't, I didn't mention how causal duality comes into the picture, but to me, it doesn't really matter. I'm in the setting of things being filtered and such, so somehow the non-unital data is the natural data to carry around anyway. But so I don't know an answer to that question, Victor, but I suspect it's hard.
Any other questions? I wanted to ask, I mean, you describe broken in a very nice geometrical way, and you exploit the geometry to get its properties and so on. But still, it looked like there should be some purely combinatorial description of it. Have you any idea how it would look?
Right. So it's hard to say. To me, this is about as combinatorial as it gets. So at the end of the day, like the real fact that we're using here is, once we have this cover, it actually turns out that, as kind of Victor alluded to, it actually turns out that the combinatorics of the cover and what it means to be a sheaf just boils down to looking at totally ordered finite non-empty sets and only surjections between them.
Oh.
So if you like, somehow the exit path category of broken looks like this category in some sense. And so the exit path category has a purely combinatorial description. So as a stratified object, it does have a purely combinatorial description. I don't know if that answers your question. Like, you know,
Yes, that's useful.
yes. But I should say somehow it's, as you know, it's the geometry that allows us to make connections with things like Morse theory and Fukaya categories.
Yes. Very nice. Are there more questions or comments? Then I think we should thank Hiro again. And of course, the discussion can continue while we prepare and wait for the next talk. Feel free to speak up.